All right, I will wait just a minute to start. I want to make sure that this is all working correctly. Okay. Well, things seem to be working, so we will hope that I have figured out how to use all of this software. So welcome, everyone, to the first weekly UCLA Planetarium show of the 2021-2022 academic year. We are, unfortunately, still virtual, but we will see about that going forward. So my name is Luke Finnerty. I am a second-year graduate student at the UCLA Astronomy Department. Tonight I'll be talking about a topic that's close to my own research, which is the atmospheres and the weather of very hot giant exoplanets. So first, I want to just start with a couple of program notes. There has been a lot of interest in when we are going to be resuming our in-person shows. So far, we have not set a date for that. We are going to decide on kind of a month-by-month basis. There is hopefully, though, going to be one exception to that, which is a special in-person show on December 1st for the launch month of the James Webb Space Telescope, which will be here in person at UCLA. Vaccination will be required. If you are interested in more updates on our events and our plans, you can check our website, which is astro.ucla.com or edu/planetarium. So tonight, I want to talk about exoplanets, and specifically thinking about the atmospheres of planets around other stars. But to do that, we first have to talk about how we find these planets in the first place. What do we get from these planets as we're finding them? And so we first were able to successfully do this in 1995. Was the first time we found a planet that orbits a regular star that isn't our sun. And today, in the 25 years since then, we've managed to detect more than 4,000. And that's a number that increases every day through things like the TESS mission and other ground-based surveys. So the main way that we detected these planets at first was something called the Doppler technique, or the wobble method. And the idea here is that it's based fundamentally on Newton's laws. So we can think about the sun's gravity pulls on the Earth, and that's what causes the Earth to orbit the sun. But for every action, there's an equal and opposite reaction. And so we could equivalently talk about the planet pulling on its star. Because the star is much more massive, so the star is here, because it's more massive, it will trace out a much smaller orbit. But because the star is very bright, we can actually detect the star, which we can't do for the planet. And so if we look at spectral lines in the star, these lines will shift slowly towards and away from us, and the amount they shift and the period over which they shift tells us about the size of the planet and its orbital period. So that was the first technique that detected 51 Pegasi b, which was the first known exoplanet. Recently, there was a Nobel Prize awarded for its detection. But it's really time intensive. It requires a lot of detailed observations of one star at a time in order to detect an exoplanet. So an alternative technique is something called the transit method. And this is really simple. So we just look at a star, we measure its brightness consistently at a relatively short period of time, and we hope that at some point a planet crosses in front of its star, blocks some of the light, and that shows up as a dip in this brightness, with the size of the dip being based on how much of the starlight the planet is blocking, so how big the planet is. So this is a nice technique because you can do it for many stars simultaneously. So most planets won't have the exact alignment that is necessary for this kind of transit event to occur. But if you look at 100,000 stars at the same time, you can still detect thousands of planets with this technique. And so this is what NASA's Kepler mission did. and what TESS is doing now. So these methods are great. They've given us thousands of exoplanets, but they're ultimately pretty limited. So, my first slide glitch. Okay. So for most planets that we know of, all of the information that we know about the planets can be summed up on this one diagram I'm showing right now. So here I've plotted the planet's mass, and this is compared with the mass of Jupiter. You could also think of this as a proxy for the planet's size. And on the x-axis, I've plotted the distance between the planet and its star. You could also think of this as a proxy for how long a planet's year is. So planets over here have very short orbital periods, and planets out here have very long orbital periods. And for most planets, this is all we get. We get a size, either a radius or a mass, from transit or RV, and we get an orbital period, and that's it. We can still, though, start to understand what's happening on these planets by comparing with our own solar system. This is what I was afraid of. Okay. Sorry, this software is still messing me up sometimes. Okay, but back to it. We can show our own solar system planets on this diagram as well, and we can compare our own solar system with what we're seeing in other solar systems. So I've done that here. And the first thing that kind of pops out is that there are no planets around other stars that we know of that are like the planets in our own solar system. So some of that is just an issue with our detection techniques. We're not very good at detecting planets like the Earth yet. It's just too small and too far away, and so we're going to need to wait for the next generation of telescopes before we can really find planets that are just like the Earth. Jupiter and Saturn, it's actually a bit of a different problem. So Jupiter and Saturn, our instruments are sensitive enough to detect these planets, but Saturn takes 30 years to orbit the Sun, and we've only been detecting exoplanets at all for 25 years. So we just don't have a long enough period where we've been taking good data in order to find these planets. So hopefully, over the next few years, as more data accumulates, we'll start to see this portion of this diagram fill out with planets that are really similar to our own gas giants. So what we do have, it's not really similar to our own solar system, but we have a large population of small, rocky or gaseous planets very close to their stars. And these are, a few times the mass of the Earth, maybe up to Neptune size over here. There's a population of large planets, of gas giants, that are not quite as far out as Jupiter and Saturn, but not terribly different, not really surprising. But then there's this population here called the hot Jupiters. And these are actually the first exoplanets we were able to detect. They are the easiest planets to find. But we were completely not expecting them. These are planets that are the size of Jupiter, but they are orbiting much, much closer to their stars than the Earth is to the Sun. So they go around their star with a year that lasts just 2 or 3 days. And this was really unexpected. Hot Jupiters are weird. This is one of the times in science where someone goes looking for something and just finds something completely not what they were expecting to see. And they're weird in a couple of ways. So first off, it's just hard to explain how a gas giant exists that close to a star. We looked and we developed these theories of planet formation based on looking around at our own solar system. And our own solar system is nice and orderly. We have a couple of small rocky planets relatively close to the Sun, Mercury, Venus, Earth, and Mars. And then further out, we have Jupiter, Saturn, Uranus, and Neptune, the gas giants. And so our planet formation theories, prior to the discovery of 51 Pegasi, of the first exoplanet, were really good at explaining how you could form a solar system like this. They couldn't explain how a gas giant would get on a 3-day orbital period, would get so close to its star that it's closer than Mercury. And this is still something 25 years later that we're trying to figure out. It's not clear. Maybe planet formation works differently than we thought. Maybe these planets did form there. Or maybe they formed further out where we think our own gas giants formed, and then through some process migrated inwards and wound up in these very close orbits. When we have these very close planets, that can cause weird effects all its own. So the first of these is tidal locking. So if you think about the Earth's moon, the same side of the moon is always facing the Earth, right? We always see it. Different amounts are lit up, but it's the same side of the moon, and that's because the moon rotates in the same time it takes to go around the Earth. So the moon is basically rotating in a way that it always stays facing us. These hot Jupiters will do the exact same thing to their star. So one side of the planet will always be facing its star, it will always be daytime, and the other side of the planet will always be nighttime. And so there's going to be weird differences. What happens to a planet when one side is always day and one side is always night? What does that do to a planet's atmosphere? Then there's just the temperature of the atmosphere. So these planets are so close that they're extremely hot. They're between 3,000 and 6,000 degrees Fahrenheit for a hot Jupiter. And so if they're that hot, we have a bunch of other weird things that we have to start wondering about. So is this hot enough that the planet's atmosphere can actually evaporate off of the planet, can escape from the planet? With this huge day-night temperature difference, is there going to be a contrast between the daytime and the nighttime that will cause winds between the day and the night? And when we have really high temperatures, really fast winds, and we're really close to the star, can that also do weird things to the atmospheric chemistry of these planets? And for all of these things, we really want to know more about these planets. We want to know more than what we get from just transit and RV measurements. We actually want to be able to look at their atmospheres. And there's a couple of ways we can actually do this. So the first of these techniques is to just look at the transit information in much more detail. And this is sometimes called a phase curve, and it's used to make global maps of the temperature of an exoplanet. The idea is that as a planet gets very hot, it emits heat, and it emits that heat in the form of infrared light. So when the planet transits, it crosses in front of its star, it blocks that starlight, and we see a big dip here in the brightness of the star. But if we look in infrared light that's sensitive to the planet's heat, then after the planet crosses in front of its star, we'll start to see more and more of the hot day side of the planet illuminated. It will have, I tried to draw it here, it will have an orbital phase. It will do something like the moon or Venus does, where we see more and more of it lit up. As we see more and more of this hot side lit up, we get more and more infrared light, and this is all coming from the planet because the star is hopefully pretty stable. Then, eventually, the planet is almost fully lit up, but it crosses behind the star from our perspective. It does the reverse of what it does when it transits. And so this causes another drop in the brightness, this time caused by the loss of the planet's heat. And so if we look at this effect, if we look at kind of the shape of this curve and how big this curve is overall, that can tell us about how hot a planet is. And so this was first done in 2007 using Spitzer Space Telescope data for the hot Jupiter HD 189733b, because astronomers have terribly uncreative names, and it will only get worse from here, I promise. So this is a hot Jupiter. It's cool for a hot Jupiter. It's only about 2,000 degrees Fahrenheit. And it's about 65 light years away. Like all hot Jupiters, it's very close, and so its orbital period lasts 2 days, a little bit longer than 2 days. And on this diagram, the lighter colors indicate hotter temperatures. So the average temperature is about 2,000 degrees Fahrenheit, but during the day, it's a couple hundred degrees warmer than it is at night. And you can see so this is the night side, this is the area that's, because it's tidally locked, this is the point that's always directly under the star, and then it kind of cools off at the poles. So what's really interesting about this, and what was unexpected about this, is there is a point, because it's tidally locked, that is always under the star. If you're standing at this point on the planet's surface, it will always be noon. The sun's shining directly overhead. There's no escaping it. It's always there. So we would expect that that's the hottest point on this entire planet. But when we go and we look at the phase curve data, the hottest point is actually shifted over. And so we interpret this as evidence for a jet stream, the way that we have a jet stream on Earth. This is winds that are blowing material that gets heated up at noon over into the afternoon, so that the hottest time of day on this planet is 2 or 3 p.m. So we can go to our climate models and we can ask, okay, well, in order to explain this offset, how fast do the winds have to be? They have to be about 5,000 miles an hour, which is crazy, right? I mean, think about, that's 100 times faster than highway speeds. What makes this kind of extra crazy is that even though 2,000 degrees Fahrenheit is cold for a hot Jupiter, it's still enough to melt silicates, which are rock and glass on Earth. So this planet has molten glass being blown around its equator at 5,000 miles an hour. And that was the inspiration for this slasher planet NASA poster. NASA made a bunch of kind of cool movie posters or kind of retro future travel posters. And I left the link on this slide. They are really cool. If you want, space-themed posters, would recommend. So this is cool, this is crazy, and it also turns out this is a pretty common thing. We've done this kind of phase curve mapping for other hot Jupiters. We see similar shifts in the hottest point that seems to suggest very fast winds of a few thousand miles an hour, and they're hot enough that we expect these kind of glass clouds, this molten glass, to be fairly common. So that gives us a temperature forecast, that gives us a wind forecast. But what else can we learn? What if we want to know about clouds, or what if we want to know what this planet is made of? Well, we can't do that with this technique, but we can use another technique called transit transmission spectroscopy. So here, again, we're going to look at a planet's transit in more detail. And the idea here is that a planet will block all of the light from the star, right? Light can't make it through planets. But it won't block, its atmosphere won't block all of the light that passes through it. Atmospheres are partially transparent. You can see that in this artist's impression, that's this kind of haziness. So some light can make it through the atmosphere, but not all light. And so if we look at what light is making it through, that can tell us something about what the atmosphere is made of. And so the idea here, the fundamental idea, is that atmospheres absorb. So I've plotted here, this is the Earth's atmosphere, and this is how much light is getting absorbed. So this is visible light, this is what we see, and you'll notice that there is very little absorption or scattering at visible wavelengths, which is good because if our eyes are going to work, we need the atmosphere to not absorb light. Otherwise, we're not going to be able to see very far in front of us, and seeing wouldn't be that useful. But as we go to redder wavelengths, if we go to longer wavelengths in the infrared, there start to be these really big absorption features where all of the light gets absorbed by the atmosphere. It can't make it through the atmosphere. We can then break this down into individual molecules. So we have water has one pattern of absorption features. Carbon dioxide has a different pattern of absorption features. Oxygen, methane, nitrous oxide, every molecule has a different set of absorption features. And so what we can do is we can look at the absorption features we see and use that as kind of a fingerprint for the presence of a particular type of molecule. As a just side note, because I think this is a cool illustration of it, this is also why the greenhouse effect is a thing. So the sun is plotted, this is the sunlight. It's emitted mostly at visible wavelengths. Again, that's why our eyes can see visible light. So light goes through to the Earth. It heats up the Earth, but the Earth gets much cooler. So most of the Earth's light gets emitted in the infrared. But because of these absorption features, there's only a very small portion of wavelengths where this light can efficiently escape, and so heat gets trapped near the surface. It's the exact same atomic physics behind kind of both of these effects. But for our case, what we're really interested in is when we have this absorption will cause the planet to appear bigger because light won't be able to pass through the atmosphere. It will all get blocked in these deep absorption features, but light in these areas that aren't absorbed will be able to pass through, and so the planet will look smaller. It will block less starlight. And so when you actually go and do this, you can get a plot that looks something like this. So these black points are actual measurements, and this is roughly visible light, and this is all the way out into infrared light, into the near infrared. And we can compare this with known molecular features. So this is the size of the planet, and the planet looks a lot bigger right here around 1.5 microns, where we know there's this big water absorption band. So this seems to be evidence that HAT-P26b, sorry, see, I can't even keep the names straight. But HAT-P26b, which is a hot Neptune, appears to have water in its atmosphere. This is a really hot planet, so that water is always going to be in vapor. There's no real solid surface, so it's not interesting if we're looking for life in liquid water. But this does show us that there's some water in this atmosphere. We can also look, if we look at optical wavelengths at visible light, this spectrum is very, very flat. And this, we think, is because of clouds. So what's happening here, think about clouds on Earth, right? Clouds on Earth are white. Unless they're very, very thin, they aren't even partially transparent. You look at a cloud and it's just white. All of the light that hits a cloud gets reflected or scattered. It doesn't actually make it through. Well, if we're doing our transit transmission technique, that's a bummer. We're relying on light being able to pass through a planet's atmosphere to our telescope. But all of this light is getting blocked. And so this really limits the ability of this technique to look at cloudy exoplanets. We can tell that there are clouds, but that's often all we can tell. Though the interesting thing is that the temperatures give us some information. So clouds on Earth, right, come from the oceans and the ground and other water sources, evaporate. That water rises into the atmosphere, it condenses to form clouds, and eventually those clouds rain out as rain onto the surface. So that works on the Earth because the Earth, right, our temperatures here in Los Angeles have been around 60, 70 degrees Fahrenheit. If a planet is 5,000 degrees Fahrenheit, water is always going to be a gas. It will never be able to cool and condense and eventually rain out. So these clouds have to be made of something else. And for hot Jupiters, the materials that actually can do this, that will evaporate, condense, and rain out, are things like glass, rocks, even metals in some cases. So we have clouds of rock on these hot Jupiters. One of the other cool things that this kind of transit transmission technique can do is look at atmospheric escape. So this is an example from the hot Jupiter WASP 107b. And so astronomers looked at WASP 107. They saw the transit. They saw some absorption during the transit. But then the planet finished its transit, and the absorption stuck around for a few hours longer. And so what this is attributed to is an actual tail of escaping gas. The planet is so hot that the gas is being blown off of the planet and into space. And so this gas is trailing behind the planet, and it leads to this absorption that can last much, much longer than the planetary transit. And if we estimate how quickly this mass is escaping, we find that for smaller hot Jupiters and hot Neptunes, the atmosphere of the planet will eventually be totally stripped away, and all that will be left will be the rocky core of the planet. So that seems to be evidence that these planets probably couldn't have formed in the place they are now, just because their atmospheres are being blown away. They're not stable. Another planet that we've done this for is Kelt 9b. This is the hottest known exoplanet. It is so hot that the surface of this planet is actually hotter than the surfaces of most stars in our galaxy. And we've measured a trail of material being blown away behind the planet, which is shown in this animation. One of the other interesting things about this planet and information that we can get from this technique is, if you'll notice, the star is rotating in this direction, but the planet is orbiting almost 90 degrees inclined to it. And this is called spin-orbit misalignment. If we look at the transit, this produces a particular variation in the star spectrum as the planet is crossing in front of it that lets us make these measurements. This is another piece of evidence that these planets didn't originally form here, because we expect that when planets form, they form in the plane of the star. So there's a disk of material around this star. Planets form in that disk. So for this planet to now be rotated by 90 degrees means something must have happened to send this planet inwards to where we're seeing it today. So I want to talk about one recent case study, because I think this is really interesting, and it's all happened in the last few months. And this is WASP 76b and the saga of iron rain. So WASP 76b is not just a hot Jupiter, it is an ultra-hot Jupiter. Its temperatures are more than 5,000 degrees Fahrenheit during the day. And these temperatures are so hot that iron will be vaporized during the day, along with other metals, things like chromium, calcium, other things that we normally don't think of being vaporized will be vapor during the day on this planet. We also know that fast winds are a pretty common feature of these very hot planetary atmospheres, and these winds can blow material from the day side of the planet around to the night side. So this iron vapor that forms during the day can get blown around to the night side, where things will start to cool off. When it cools off, that iron can condense, it can form clouds, and it can eventually rain out, as depicted in this artist's impression, droplets of molten iron rain. The question is, does this actually happen? Well, in 2020 and 2021, two teams reported evidence that it does. So what they looked at here is, does iron change over the course of the transit? So ingress is the start of the transit, and at this point, we are looking mostly at the morning atmosphere of the planet. At egress, that's exit, we're looking mostly at the evening atmosphere of the planet. So if this iron is being vaporized over the day and then raining out at night, and then in the morning there's not much iron in the atmosphere again, we would expect to see a difference between this ingress signal and this egress signal. We would expect to see a difference in the iron observed in the morning versus the evening. And indeed, both groups actually see something like that. And this kind of offset seems to be consistent with iron being blown around from noon over to the night side. So the picture is something like this. As the planet's coming in, so the iron, we start to see iron in kind of late morning, and then it gets formed mostly around noon and then blown over to the night side. So at ingress, we see the planet like this, but as the transit goes on, we're looking through more and more of this night side, or this evening, iron signature. So this seems pretty convincing, but atmospheres are actually really complicated. So another group, and this paper was published just in the last few months, asked, okay, well, is there another process? Is there something else in this planet's atmosphere that could be causing this instead, that could cause something that looks like this? And so they went to their atmospheric models to their theoretical models, and they started playing around with different parameters. And they found that, in fact, there are a bunch of different settings that can produce very similar data to what we actually observed, but without this iron distribution, without this need for iron to be vaporized in the morning and then to rain out in the evenings. And so the takeaway here is atmospheres are really complicated, and there's a lot we still don't understand. We've talked today about winds and clouds and chemistry, and those all impact our observations, right? Those all have different kind of ways they can mix and interact. Something I've completely left off so far is magnetic fields. And that's actually this diagram. Magnetic fields are a whole other can of worms that we haven't even really started to touch, even in theory. There's a lot of work to be done in understanding how magnetic fields will change planetary atmospheres. And one of the challenges in this is that in order to interpret our observations, we really need good theories and models, right? In order to understand whether our observations mean there's iron rain, we need to understand what types of scenarios can produce those observations. And we're really limited in this because our own solar system doesn't have any hot Jupiters that we can easily compare to. That's good for me, though, because there is a lot of work left to be done on trying to understand these planets and these systems better. There's a lot more theoretical and observational work that we still have to do to really understand these systems. So I hope that I have made the case that these planets are really cool and their atmospheres are really cool. But they're not the planets we're most interested in, right? What we're really interested in are planets like our own. And so this is an artist's impression of the TRAPPIST-1 system. This system has 7 small planets that are observed to transit its star. It's a relatively small and cool star. And 3 of these planets are at the right distance where they could conceivably maintain liquid water on their surface. So these are the planets we're really interested in, right? These are the planets where we want to know if there's life. And hot Jupiters, these studies of hot Jupiters, can help us eventually answer that question. So hot Jupiters are big, they're bright, they're close to their stars. They're really, really easy to actually find and characterize in much greater detail. So the hope is that by starting off with these interesting and easy cases, we'll develop new techniques, we'll start to get better theories, we'll understand how to interpret our data, and then apply that to other systems like TRAPPIST-1, as we get this next generation of telescopes, such as James Webb and TMT. So I want to stop there and ask if there are any questions, and then I'll move on to talking a little bit about the night sky as we can see it today in Los Angeles. My stream is on a little bit of a delay, so there might be an awkward pause here. It's okay, I need to drink water anyways. So the largest, that's an interesting question. So largest can mean a couple of things. So largest can mean mass. And mass, there's actually a little bit of a controversy over how massive something has to be before it stops being a planet and starts being what's called a brown dwarf. And the generally accepted kind of definition that we're coming to slowly is that the maximum mass a planet can have by definition is about 13 times the mass of Jupiter. In terms of radius, planets, this is one of the other cases where hot Jupiters are a little surprising. So we expected that planets wouldn't get much larger in radius than Jupiter. And this is because as you add more mass, the gravity increases. And so even though there's more material, it's held more tightly and the planet size can't increase that much. What we're actually seeing, though, are hot Jupiters that are 1.8 times, almost twice the radius of Jupiter, which is not really something we expected to see, and it's still an open problem about how those planets actually get to the size they get to. This is one of those cases where people are shrugging and saying, well, maybe it's something to do with magnetic fields, because that really seems to be the best answer that we have right now. It's still an active area of research. Okay, well, now we reach the point where I need to change screens, and this is going to be dicey. So normally this is where we would be in our planetarium at UCLA with the really nice projector, so you can lean back and it looks like you're seeing the night sky in Los Angeles. We can't do that virtually. We're stuck with the 2D version, but the 2D version is actually really cool. So this is actually free software called Stellarium. It has Windows, Mac, and Linux clients. So you can go and download it and play around with it yourself. And the cool thing is that not only does this let us kind of look at the night sky, it also lets us simulate having a pair of binoculars or a small telescope, because we can just zoom in and we can see what we would see that way. So this is the night sky in Los Angeles. I think it's actually right now. Yep, this is simulated right now in real time. So I'm currently looking south, and if we look southwest, there is a very bright star, and that's Venus. And you can actually see Venus even during the evening or during the daytime if you know where to look. It'll be a little bit higher, it'll be maybe up here, but you can see it around sunset. So if you're out for a walk in the evening, I would definitely be looking for it. Venus is a cloudy planet, so if we zoom in on Venus, if we simulate having a telescope, we don't really see much. We see some slice of Venus, the same way that we see slices of the moon. Venus has phases, but that's really all we see. We just see this kind of hazy crescent. So if we want to see something in a little bit more detail, we can zoom out and we can turn our attention south. And we've lucked out tonight because we can see both Jupiter and Saturn. So the moon is here. The moon's almost due south right now. And I think it's at first quarter. So if you have a pair of binoculars, you can see the leading edge of the moon. And you can actually see, so you zoom in, so the Sea of Tranquility is right around here. This is where Apollo 11 first landed. And if we zoom out, and then we go just a little bit above the moon, we have Saturn. So Saturn, if you get a pair of binoculars, and I should say, this is very optimistic for Los Angeles light pollution, so maybe this is more like the Mojave. But if we zoom in, we'll see Saturn. We'll see the rings. You can even see a gap in the rings, and you can maybe see a couple of the moons. Titan is the one that's easiest to see, and Titan is a really cool moon too, because it has an atmosphere that's actually thicker than the Earth's. Although again, it's cloudy and hazy, so it's kind of a pain as far as observers are concerned. If we move over, now I'm going to zoom out. So this is Saturn. Saturn is just above the moon and a little bit further south. Jupiter will be a bit to the east of Saturn, and Jupiter's pretty substantially brighter than Saturn. So Jupiter, all you really need for this is binoculars. But if you zoom in on Jupiter, you will see 4 dots. Tonight it's 2 to either side. And these are the Galilean moons, named for Galileo, who was the first person to see these. So these are Ganymede, Io, Europa, and Callisto. And what's cool is that if you come back tomorrow, these moons will all be in a slightly different spot. And so if you come back night after night, you'll see these moons orbiting. They'll go around Jupiter. And this was, when Galileo saw this, this was the first evidence that anything in the universe revolved around something other than the Earth. And so this was kind of a key component in our development of, okay, the sun is at the center of the solar system, and the planets go around the sun, and the moons go around the planets. It's an experiment you can do yourself with a couple of nights. If you have a telescope, you can also zoom in and see some structure in Jupiter, so you can see a couple of these bands. And if you're lucky, in terms of the weather and in terms of the time of day on Jupiter, you'll be able to see the Great Red Spot with a fairly small telescope. So those are the planets we can see tonight. And if you are in Los Angeles proper, you're probably not going to have much luck with anything else. But if we go out into the desert, out to Joshua Tree or somewhere, you can also get a view of the Milky Way. So the Milky Way is right here. It's kind of between Venus and the moon right now. And you can see, so Sagittarius is here. It's this kind of teapot. And the nice thing about having Stellarium is I can go and turn on some constellation lines. So when you're trying to navigate the night sky, my, best recommendation is to look for something that you can always kind of recognize. Look for some kind of geometric formation of bright stars and then reference yourself to there. So we can do that. We can find Sagittarius. And this is the famous kind of teapot. And Sagittarius overlaps with the Milky Way, and the center of our galaxy is actually right about here. So this is Sagittarius A star. You can't see it with the naked eye, but you can see the band of the Milky Way in that area. Recently, UCLA astronomer Andrea Ghez received the Nobel Prize for confirming the black hole at the center of our galaxy that's right around here. And so this is very visible during the summer. So a lot of UCLA astronomers they're observing during the summer where they can actually see the Milky Way at higher elevations. Right now we're kind of late in the season for it because it's setting fairly soon after sunset. So the last thing I wanted to point out tonight is now east and northeast. There's a W, that's Cassiopeia. And then we have the square of Pegasus. And then between Cassiopeia and the square of Pegasus, there's this kind of fuzzy blob right here. And you can see this under decent conditions with the unaided eye. You don't need any kind of telescope or binoculars, although it will make it easier. And this is the Andromeda Galaxy. So if we zoom in, we'll start to see that this is actually a disk. It's a galaxy like our own, and it's 2.5 million light years away. It's the closest large galaxy to us. So this is a fun one. If you're in a dark spot, you can see it. Sometimes for these more extended objects, you actually don't want to look directly at it. You want to look at it kind of out of the corner of your eye, and you can get a bit of a better view. So I think that is what I wanted to talk about in the night sky. This is a little bit of a weird time of year because we haven't yet reached evening constellations, but we still have some of the summer up. So I think I'm going to leave it there. I guess I will stick around for a couple more minutes if there's any questions, but I want to say thank you to everyone who came out for the first of our virtual series this year. We will be doing these every week. Hopefully we'll be back in person at some point, but we do definitely want to think about how to continue these virtual presentations because they have proved there has been interest, so we want to keep doing that. So yeah, thanks everyone who came. I'm going to end the stream.